Hello and welcome back to Introduction to General Relativity. In today's lecture, we're going to solve Einstein's field equations for the case of a homogeneous and isotropic spacetime. Well, more properly, we're going to commence the solution of Einstein's field equations for a homogeneous and isotropic universe. So that brings us to the topic of the dynamics of a homogeneous and isotropic universe. How does such a universe evolve from its inception, so to speak, to its final moments, if there are any? So what we're going to do is we've only described in the previous lecture half the story, right? We've described the structure of the metric of a homogeneous and isotropic universe, and we've reduced the task of solving this metric in Einstein's field equation to that of solving for a single scalar function a of tau. Now we've got to describe the other half of Einstein's field equations, namely the stress energy tensor. What's the stress energy tensor we're going to assume or attach to a homogeneous and isotropic universe? So it's a highly idealized model. So we're going to idealize galaxies in this model to grains of dust. And we're going to further assume that these galaxies really move, they don't have much initial velocity of their own. In fact, they're going to move on world lines of isotropic observers. Now, these galaxies will have some fluctuations in their velocities. You know, the universe isn't completely isotropic and homogeneous, but in order to model the stress energy distribution of the universe, we're going to assume in this highly simplified idealized model that the fluctuations of these galaxy velocities is very small. Is much smaller than any other quantity, in particular the speed of light. And so in this way we're going to neglect any form of pressure in modeling the stress energy tensor of the matter of our universe. And in that sense it's pretty easy to write down the stress energy tensor. You know, the stress energy tensor is that of just a homogeneous uniform gas of particles with no pressure. So this is just the stress energy tensor of the galaxy, of the matter content, the visible matter content. And it's super simple. We just take the matter to move on the world lines of isotropic observers. Easy. Where rho, of course, is the density of the average density. So you smear out the galaxies until they're a homogeneous soup. So that was easy. We could throw that into Einstein's field equations right now and try and solve things, but we wouldn't be modeling the physics of our universe quite correctly yet, because there is more stress energy, mass energy content to our universe. In fact, there's at least one other field that will in fact play a role in the evolution of our universe, and that is the electromagnetic field. So there is experimentally determined background thermal radiation throughout our universe. It's at approximately at a temperature of 3 Kelvin, and we're going to model this background radiation also as a perfect fluid. It's a somewhat advanced exercise, pretty advanced exercise involving a little bit of statistical physics to argue that the thermal state of the electromagnetic field can be modeled with a perfect fluid stress energy tensor. I mean, there aren't so many options, right, in this situation of homogeneity and isotropy. So there aren't so many symmetric, homogeneous, isotropic four tensors that you can write down. And so you pretty much reduce to just describing things in terms of diagonal 4x4 matrices where the three spatial components are equal and the temporal component is potentially unequal. So we use for the stress energy tensor of the radiation field the perfect fluid stress energy tensor, where in this case the pressure of the radiation field is exactly 1/3 of the density. And thus the total stress energy tensor of the universe is, as I just mentioned before, as general as it can be, while respecting these additional symmetries. And that is, it has this perfect fluid form, but where P and rho are appropriately adjusted to incorporate the galaxy matter content and the radiation matter content. And so I'm going to just say most general is, and I think I can safely leave that as an exercise for you. What is the most general stress energy tensor you can write down? Well, it also has essentially perfect fluid form, but rho and P are no longer just P rad and rho rad and P galaxy and so on. They have to be adjusted, those constants, to incorporate these contributions. So that's extraordinarily simple stress energy tensor. It's a diagonal stress energy tensor if you look at it in the coordinate system we've been working in, and the spatial components are all equal. And now what we're going to do is we've got the right-hand side of Einstein's field equations. So now we're really in a situation where we can write out the full equations of motion for our universe that we live in. So no perturbation theory here, no approximations here. We're going to go for a full solution today and in the next lectures. And Einstein's field equations, well, what do we need? Well, we need the Einstein tensor G, big G. We need the stress energy tensor TAB. So we have the metric, we have the stress energy tensor, and I've added on here an extra term called the cosmological constant term. That's a consistent, one can add this equation, add this term to Einstein's field equation. Einstein himself also added this equation, this constant term to the field equations, although he, for very, very different reasons, which if you're interested in the history of general relativity, you can look up. So we've added an additional term, lambda, the cosmological constant. And it turns out that although it was hoped that lambda by Einstein, who added it in order to model an eternal universe, it was later hoped that lambda would be 0. Well, that's not the case. The observations now favor a non-zero value of lambda, and these observations have essentially been independently verified now. And what do we need it for? Well, we need to account for the observed cosmic background radiation. But also very recently, this term, the non-vanishing of this term, was also independently, largely verified by the dark energy surveys, which have just been completed or just begun. We're just beginning to analyze the data from these dark energy surveys. So the cosmological constant is here to stay. We have to have it in order to match, to model the universe that we live in. So why not, for this rest of these next coming lectures, include it in our solution of Einstein's field equation? It turns out to be rather easy to do so. It just effectively adjusts, it acts like a negative pressure term. So in principle, so how hard is it to solve Einstein's field equations? Well, you know, in principle, we need to solve 10 simultaneous, coupled, nonlinear, partial differential equations. And you know, and why 10? Well, the variables in Einstein's field equation is the metric. The metric is a 4x4 matrix. A 4x4 matrix has 16 terms, but if it's a symmetric 4x4 matrix, which it is in the case of our space-time that we live in, then only 10 components are actually independent, so you only need to solve for 10 things, 10 variables. Now, 10 nonlinear coupled PDE is ridiculously complicated. I mean, most of your career in physics, let's say, you know, unless you've been heavily involved in fluid mechanics or something, has been mostly occupied with linear partial differential equations or ordinary differential equations. You've probably in fluid mechanics encountered nonlinear partial differential equations, but not like 10. You have the worst case scenarios like Navier-Stokes equation. And so this is a monstrous system of complexity far exceeding anything that you're likely to encounter in any other branch of physics. And so you can't hope to have a general solution. You know, there's no Green's function, nothing's going to save you in general. It's absolutely an orders of magnitude more ambitious a task to solve these equations of motion. However, you can either use perturbation theory, as we have done in the previous lecture, or you can exploit symmetry, so to reduce the number of equations you have to solve and keep reducing until you hopefully just get to some one nonlinear or ordinary differential equation, and that you can solve, you just integrate by quadratures or whatever. And that's exactly what's going to happen here today. We're not going to need to solve 10, thank goodness, because of homogeneity and isotropy, we're going to get away with a lot less. It turns out only 2 equations are in fact independent anyway. And the argument for this is, well, note the following, right? The vectors which you get by contracting the Einstein tensor against the UB, the tangent vector going in of the isotropic observer, and the stress energy tensor with UV, these cannot have spatial components. That's due to isotropy. And similarly, if you restrict your attention to sigma t, one of these slices, then you can make a very similar argument that we made for the Riemann curvature tensor of HAB, you know, that was the argument involving diagonalizing matrices and symmetries and degenerate eigenvalues. It implies that the three-dimensional Einstein tensor is proportional to the identity. Otherwise, you could select out a distinguished vector. So the off-diagonal terms of star, they vanish. So if you recall star as Einstein's field equation with cosmological constant. And the diagonal space components are equal. These are effectively induced by the eigenvalues of GA. These effectively induce the eigenvalues of GAB on sigma t. And of course, homogeneity implies that the space-time components vanish. And so we're left with just two independent components from star. And we're going to write them like this. G tau tau plus lambda G tau tau equals 8 pi rho. Just look up the stress energy tensor and the time or tau tau component. And G star star plus lambda G star star equals 8 pi p. And I got to tell you what the star notation means. And this G tau tau. Well, G tau tau is easy to explain, right? It's just GAB, where you put in the tangent vector of the isotropic observers, and G star star is just any spatial component that you get by contracting with a unit space-like vector. And what we're going to do is, well, we've got to do the calculations still, right? I haven't yet completely trivialize this problem. We've got a system of two equations now, but the metric is like highly non-trivially embedded in the Einstein tensor. I mean, it's explicitly there in the cosmological constant term, but in the Einstein tensor it's sort of buried in a nonlinear way. So to carry out the subsequent calculations, we're going to have to work out the dependence of the Einstein tensor on the metric. And to do any computation in physics, you will need to choose a basis, and you will need to do some hard work. You can't, you know, basis free, doing things basis free and coordinate free is wonderful for deducing logical consequences of statements, but is hopeless for doing any real calculation where you want to model some physical process. So to actually carry out a calculation, we're going to need to do some calculating. So we're going to have to obtain the explicit form of our metric, and it turns out to be rather convenient to write the FLRW metric in the following form. It's just a little exercise for you. And it's in this way we can consistently cope with all three possibilities of the constant big K. And how do we do that? Well, where little k equals +1 is corresponding to the sphere, three spherical sections. K equals 0 equals the Minkowski space. or flat, well, not Minkowski, but flat space sections, and little k equals -1 is the hyperboloid case. And we're going to take this is the form of the metric that we're going to use in our subsequent calculations in the following lectures. We're going to take this metric, we're going to calculate the associated Christoffel symbols. We're going to then, from the Christoffel symbols, build the Riemann curvature tensor, the Ricci tensor, the Ricci scalar. We're going to substitute all these functions into the two remaining independent components of Einstein's field equations, and we're going to arrive at some nonlinear differential equations, which we will then solve. And we will be able to solve them remarkably. But that is a story for the next lecture. That's it for today. Thank you and goodbye.